In this work, we quantify the amount of information used by common state-of-the-art convolutional neural networks to make predictions. We found that set networks discard a large proportion of the input signal. Moreover, the signal that has been dropped depends on its spatial position and not on its semantics. Imagine you have to classify images of cats and pineapples. In order to do so, your task gets easier the more information you have about each individual image. Conversely, the task will be more challenging if parts of the images were missing. Given the overwhelming and well-established success of today's convolutional neural networks for classification of natural images, it is reasonable to expect these models to make use of most of the information contained in each input sample. The main goal of this work is to quantify how much information is effectively being used. In other words, how much information can be taken from the image without affecting the classifier's performance. To this end, we propose a two-stage training scheme for an image autoencoder as follows. First, we train a deep autoencoder with the usual unsupervised loss. We used the large YFCC 100 million dataset to train a segnet autoencoder, achieving a low and stable reconstruction loss. An interesting consequence of using such a large training set is that the autoencoder can be trained using a single epoch. In contrast, the same training scheme using ImageNet shows a more unstable and biased representation. Once the autoencoder has been trained, the decoder enters a fine-tuning stage that uses gradients flowing from a fixed, pre-trained classifier. Note that both the encoder and the classifier are kept fixed. That is, their weights are not being updated during the second phase. Once the decoder has been fine-tuned, we measure the accuracy of the classifier when using reconstructions from the resulting fine-tuned autoencoder. In our experiments, we tested using ImageNet on 5 well-known image classifiers: LeNet5, AlexNet, VGG16, ResNet50, and Inception v3. We see that there is no compromise in performance when using the fine-tuned autoencoder, as opposed to using the original segnet trained in stage 1. We say that the autoencoder has learned to decode all parts of the input images that are useful to the classifier. In other words, it preserves the signal contained in the image that is used by the classifier. We can now have a look at the different reconstructions when a fine-tuned autoencoder has been trained for a particular classifier. The LAB histograms are also shown to better compare changes in the decoder introduced by each classifier. We see how original segnet reconstructions are quite accurate, yet the classification accuracy when using those drops substantially. Slight changes are introduced for VGG and Inception, although the distribution of color is in general fitting the original one. In contrast, AlexNet and ResNet50 show a well-defined checkerboard-like pattern where pixel information has been replaced by rather constant values. Note that such pattern is constant within the entire image and across all reconstructions. Here are some other randomly selected samples. Due to the constancy of set reconstruction patterns, we can conclude that the information contained at those pixel positions is now less than in the original sample. More generally, the information contained in the reconstructions decreases, whereas the corresponding classification accuracy does not. To measure the amount of information that has been lost during the reconstruction process, we compute the normalized mutual information in 2 different ways. The inter-class information, shown in purple, is the information between different samples, belonging to different classes. This is expected to follow random chance. Higher inter-class information serve as evidence of a constant pattern in the reconstructions. In contrast, the intra-class information, shown in green, measures the similarity between the original input and a given reconstruction. High intra-class information corresponds to reconstructions that are more similar to the original image. Results of measuring intra-class information show a correspondence with the previous qualitative assessment of the reconstructions, where AlexNet and ResNet 50 have the strongest constant patterns, followed by Inception v3 and VGG 16. Note that the amount of information preserved or used by a classifier doesn't directly correspond to the classification accuracy. We further investigated the correlation between the information preserved between classifiers. In other words, we want to know if the information that is useful to one classifier is also useful enough for a second one. Concretely, we can define a measure of usefulness by measuring the drop in performance of one classifier when reconstructions from a second one are used instead. If said drop is above a threshold, we say that the signal of the second classifier is useful to the first one. Here's an example where the accuracy of a classifier I is measured using reconstructions coming from an autoencoder fine-tuned on a second classifier J. We see some highly compatible and some non-compatible signals across the array of possible combinations of the three higher performant networks in our previous tests, that is, VGG, ResNet 50, and Inception v3. By setting a threshold of 94% for the notion of usefulness, we can construct a lattice as follows. A node represents a formal concept in the hierarchy of signal usefulness. Intuitively, a node shows a particular stage on the hierarchy of said formal concepts, where classifiers, which appear always on the top of a node, can use the signal from all autoencoders, which appear on the bottom of each node, connected below. In other words, the signal of the classifiers whose autoencoders appear lower in the lattice are more generic or useful to more classifiers. Conversely, the signal of the classifiers whose autoencoders appear further up in the lattice are more specific to their own classifier. We can see how the signal used by VGG can be used by both ResNet 50 and Inception v3, aligning with the mutual information experiments from before. However, the signal used by Inception v3 is quite specific to Inception v3 itself, although it's one of the networks that preserves most of the original information. Similarly, the limited amount of signal used by ResNet 50 is enough for Inception v3 to perform well nonetheless. These analyses show some emerging counterintuitive properties of these networks that have not been factored in when designing them. Intuitively, one could expect a network to make better predictions when more information is effectively being used. Understanding the idea of useful input information can lead to better, more principled design of neural network models. We found multiple instances in the literature where different neural networks were used, but their resulting differences were only superficially described. The tools and framework proposed in our work suggest that the results from existing research not only align with our findings, but can also be better understood and analyzed. We also find that the two-stage training scheme proposed in our work induces an emergent resiliency to noise in the autoencoder. We are now focused on further understanding of the properties of the autoencoder itself, as well as the behavior of the classifiers when the architecture of the autoencoder changes. We are also interested in finding out what part of the metaparameter space is most correlated to the use of more or less input signal. For more information, please check out our paper. All the links to the archive draft and the paper's landing website can be found in the description below. Thank you for watching.